Welcome everyone. As you can see, the question in front of you is dealing with an iron core transformer. It's an ideal transformer. Ideal ka matlab hota hai there are no heat losses. Explain why the supply to the primary coil must be AC and not DC. Because you know the principle is that you must have a changing magnetic flux. So you need a changing magnetic flux. Of that changing flux comes from a change in current. So that an EMF is induced in the secondary coil, because you know that EMF is rate of change of flux, so you need a changing flux. Then for a constant input power, the output current decreases if the output voltage increases. So basically you have to explain that P is equal to VI. If P is constant, then V is inversely proportional to I, which means that if current increases, voltage will decrease. And just remember that you must mention that this is the output power, which must be kept constant. Next, you have the current versus time graph, and they're asking you for flux time. So current does exactly what flux will do. So the same shape, if I can draw it, there we go. And EMF is rate of change of flux. So if this is a sine curve, this has to be a cosine curve. So therefore, I think one cycle should be enough, because they haven't mentioned how much time, for how long. And remember that this point and this point must be in sync. When a sine curve is at 0, the cos curve is at maximum. That's the phase difference between a sine curve and a cos curve. And I think, we've answered these questions. And what's the phase difference between the primary coil and the EMF? That's always 90 degrees, or pi divided by 2 radians. Question number 2 deals with radioactivity. And for the first part, if you look at it closely, manganese decays to form iron. So iron का mass बढ़ना चाहिए और manganese का mass कम होना चाहिए. और उसने iron versus time graph दिया है, so iron का mass बढ़ेगा. Now he said that the half-life is 2.6 hours, and you've got 1.4 micrograms of manganese at the start. So 1.4 micrograms of manganese at the start. After one half life वो आधी हो जाएगी, तो 0.8 पे आ जाएगी. तो उतने ही टाइम में आयरन ने फॉर्म होना है. आयरन 0 से स्टार्ट करेगा और 0.8 ग्राम्स पे पहुंचेगा, जब मैंगनीज 1.4 से 0.8 पहुंचेगी in 2.6 hours. So this is 2, this is 4, so 2.6 would be somewhere here. And then you just draw a smooth curve through it and make sure you flatten it out at 1.4, because this curve is going to flatten out over here like this if it was for manganese. But it's for iron forming, so the curve goes up. Now this part, the answer is 1.5 in 10 to the power 16. And how do you do it? You use the formula for calculating the number of moles, which is mass over the MR. The mass is 1.4 into 10 to the power minus 6. It's given over here. Divided by the MR, which is 56, you get the number of moles. Number of moles into Avogadro's number would give you the number of particles that you have, or the initial number of atoms that you have. Next, the initial activity. The formula is A naught is equals to lambda into N naught. N naught you initially found out in the previous part, which was 1.5 in 10 to the power 16. Lambda, which is decay constant, is given by ln2 over half-life. Half-life was 2.6 hours. Convert that into seconds, because you have BQ over here. Becquerels means per second. So ln2 over half-life in seconds into n naught, the value, and the answer is 1.11 into 10 to the power 12. Then they say determine the time at which the mass of iron over mass of manganese is manganese 56 is 9. You must understand that manganese decays to form iron. So manganese decays to form iron, and this ratio, if this is 9, it's telling you that iron is 9 and manganese is 1. That means the total was 10. So out of 10, 1/10 is owned by manganese and 9/10 is owned by iron. So I use the equation n is equals to n naught e to the power minus lambda t. So that means that we're trying to find out the time at which 1/10 of manganese is left, basically. Because manganese was decaying, so how much manganese is left? 1/10 is left. 9 is the one which is forming, and this equation is the one which decays, right? Manganese decays, so you have to apply it on manganese. Now the question is, they're asking for the time at which you have 1/10 manganese left. How long did it take for you to get there? So n, you'll replace that with 1/10 of n naught. N naught is your initial number. Initial numbers will get cancelled. So 1 over 10 is equals to e to the power minus lambda t. Take the natural log on both sides. And this is how you solve. The answer will be in seconds. Convert that into hours and get 8.63 hours, which is the answer over here. Alright, so in this question, what is meant by an ideal gas? PV over T is constant for all values of pressure, volume, and temperature. Then they're asking to calculate the number of moles, so you use PV is equals to nRT. Pressure and volume are given. Make sure the temperature is in Kelvin, and you get 3.73 moles. Now, in this part, they're saying that the pressure in the tire has to be increased, and in each stroke, you pump in 0.012 moles of air. Calculate the number of strokes of pump required to increase. So they're not asking you to go from 0, they're asking you to go from this pressure to a new pressure. The number of strokes of pump required to increase the pressure from this to this. That means by default you have these many moles of air in the car tire, and you have to go up from here to a new number. You have to calculate how many strokes do you have to pump in to get from 3.73 to the new number. So first of all, you calculate what the new number of moles are. So PV is equals to nRT. So pressure is 3.4 in 10 to the power 5 into the volume 3.1 in 10 to the power minus 2 is equals to nRT 8.31, 27 plus 273. So the number of moles are 4.23. Now, the change or the increase in the number of moles is 0.5, and on each stroke you pump in 0.012 moles. So how many strokes do you need? So do 0.5 over 0.012, you'll get around 41.66, but 41 would be a smaller number. You would need more moles, so you round it up to 42. Now here they're saying calculate the angular frequency. Angular frequency is 2 pi f. Frequency is given, just multiply, you'll get 8796 correct for sig figs, and you get 8800. Then they're asking for maximum acceleration. Maximum acceleration is omega square a. Omega square x is the general version. When you put x equals to a, then you get maximum. So your maximum would turn out to be 6189. Again, correct for sig figs. You get 6200. Then they're asking you for an acceleration versus displacement graph. So straight line through the origin with a negative gradient. Make sure that this length and this length, they're equal. So they cannot be unequal. They have to be equal. So make sure that you measure it properly. And then you label this. You'll call this as maximum acceleration in the positive direction, maximum acceleration in the negative direction. This is the negative amplitude, and this is the positive amplitude. These 4 points are key. Then they say calculate the value of the displacement if the speed of the cone is maximum. So whenever the cone passes the mean position, the speed will be maximum. So at mean position, your displacement is 0. Calculate the maximum speed. Maximum speed is given by omega a. Omega is this, a is this. Given in the question, your answer should be 0.70 meters per second. So what is magnetic flux density? It's given by this formula. It's the force per unit length acting on a current carrying wire placed perpendicular to a field. Now, whenever you have a flux density given and going through an area A, and they ask you for calculating the flux linkage, first of all, in linkage, you always have a number of turns. So the general formula for flux is BA, but when you have linkage, then you do NBA. And one more thing that you have to be careful of is that the magnetic field strength or the flux density must be perpendicular to the area. So this is going at an angle, right? So when you make its components, I've tried making it at two places. So one component with this way and one component with this way, and this component is perpendicular because this is going to be parallel in the same plane as this area, and you want the component to be perpendicular. So that is b sine theta. So therefore, the flux linkage will be given by NBA into sine of theta. Next, they're saying what is Faraday's law? Faraday's law is EMF induced is proportional to the rate of change of magnetic flux. This is a magnetic flux density versus time graph, and they're asking for EMF. Now, EMF is the rate of change. Rate of change means gradient. So the gradient of this line is 0, so the EMF would be 0. The gradient of this line is, let's say, +2, so the EMF would be +2. Just give it a random number. And this line, the downward sloping line, it seems to be more steep than the +2. So let's say that the gradient is -5. It seems to be twice as steep almost. So 2 or 2.5 times. So what I did was I gave it a value of -5, and then the EMF should be -5. And that's how you do it by numbers, because EMF is the rate of change of flux, and this is your flux density. So the gradient, rate of change means gradient. So the gradient of this graph would give you EMF. Next, you have radioactivity, binding energy per nucleon versus mass number. This is the most stable point. This is iron 56 over here. What is meant by binding energy? Energy required to completely separate the nucleons in a nucleus to infinity. And then you have to mark the most stable. Then they're asking for the number of neutrons in this equation. So you got 235 plus 1 is equals to 142 plus 90 plus x into 1. Because I don't know how many neutrons I have. And if I can find the value of x, the value of x turns out to be 4. Because you know, in a nuclear reaction, the mass number must be conserved. So the total mass of the reactant must be equal to the total mass of the products. And then in this part, they're saying this is the data for binding energy. Calculate the energy in mega electron volts released in this fission reaction. So you just do delta E is equals to. Now, what are your products? Your products are xenon and strontium, right? So this is the binding energy per nucleon. How many nucleons do you have? 142 nucleons you have. So 8.37 into 142 plus 8.72, that's strontium. It's binding energy per nucleon. And how many nucleons of strontium do you have? 19 nucleons. By nucleon, you mean the protons and the neutrons. So you've got these many protons and neutrons in strontium, these many protons and neutrons in xenon, and add them and subtract it from uranium 235's energy, which is going to be 7.59 into 235. So you get 1189 plus 785 from here, minus 1783 from here, and subtract them, and you get 190 mega electron volts. Now they're asking for the mass equivalent. So you do 190 into 1.6 into 10 to the minus 13. This is for the conversion to joules, because you know 1 electron volt is 1.6 into 10 to the minus 19 joules. So 1 mega electron volt would be 1.6 into 10 to the minus 13 joules. So you've got this many mega electron volts. So you convert the mega electron volts into joules by multiplying with this number, and mc square, c is speed of light, 3 into 10 to the power 8 whole square. And the answer that you get is 3.4 into 10 raised to power minus 28 kilograms.